So today I wanted to continue the previous lecture in the sense that I would like to discuss some possible extensions of the algorithm that I presented and some, well, maybe not simplifications because that was the simplest that I could state, but some possible extensions and variants of the algorithm for word equations. So to okay, so improvements in general. So to recall, the algorithm worked for word equation, which was of the form u equals v, sometimes written as u equals v in small letters or capital letters, no difference. And what we did is that we listed the letters which are in the equation and chose either to compress some pair of letters, so some AB, or all blocks of a letter A, again for something which was for a letter which was in the equation. Okay, and it could be that we not deterministically guessed whether this AB or A blocks are crossing or not. Crossing meant that part of the occurrence of, well, AB or A block was inside the variable and part was outside. So like this, when this was substituted for a variable. And if this was the case, then we popped those problematic letters. So just shortened the substitution for the variable and I'll put this letter explicitly in the equation. Of course, did it for all the variables, and then compress it because then this crossing problem was no longer there. And the fact that this is sound in the sense that if we arrive at the solution, then indeed there was a solution, is relatively easy to show. What's the problematic part, and somehow the non-obvious one, is that to show actually the p-space bound. Okay, and this was shown by saying that either there's something non-crossing pair, which of course reduced the space occupied by the equation, or by saying that there are not too many crossing pairs or crossing blocks, so we could choose the one which appears often enough and then compress it. And there was some space bound, which was, well, some concrete space bound that we could show, which is more or less 8 times n square, where n is the size of the input. Okay, so one of the things that we would like to add to word equations are constraints. So in general, what are the constraints? Then the simplest one that you could think of is that we have some conditions which are just put on the variables. So we specify some languages in some way and then say that we want the substitution for x to be inside some language or outside some other language. And we could specify many such constraints. For instance, we could say that we want this to be, well, this art could be a context-free language, and then unfortunately word equation become undecidable. And this is relatively easy to show because well, you do not need any equation whatsoever. We just say that x is in one context-free language, x is some other context-free language, and we ask whether the equation x equals x is satisfiable, which means that the intersection of those two context-free languages is non-empty. Okay, some other constraints which are also undecidable are letter counting constraints, which means that we have access to the number of letters inside A. Those constraints cannot be written in this simple form, but there is some arithmetic on the number of occurrences of A in different variables. And again, this is expressed enough to actually show to be undecidable. The largest class of constraints for which we can show the decidability are the regular constraints. So those languages R and R prime, which we considered before, are regular languages. Okay, and although those looks like relatively simple, but they, on the other hand, they can express some simple properties which seem useful, like the substitution for x does not use A, or there is an AB somewhere inside the substitution for x. Or there is no AB inside the substitution for x. And actually, those constraints will specify that some forbidden subpatterns are not there. Those are actually quite useful because they are useful for when you want to solve some equations in groups, then those forbidden factors are factors which somehow cancel out. And in some cases, those regular constraints allow you to extend the word equation from some simpler scenario to some more complex. Excuse me, I need to turn off the phone. to generalize to some more complex scenarios. For like the open problem that I would like to state is that we do not know what happens if we have access only to the lengths. So if we just say that the substitution for x is, for instance, larger than the substitution for y, or that the substitutions for x and for z are of the same length, if we have lists of such constraints, then it's unknown whether this can be solved or not. As all the previous solutions, they do not work in this, and they cannot cope with this scenario. Okay, so when we look at regular constraints, then there are of the form that x is, well, as written before, so regular constraints, and we just list the simplest way we would like to use them. Well, the most convenient way that we would like to use them is to say that substitution for x is inside some regular language or outside of some regular language, and potentially this is specified somehow. So the most expressive option is that we use the non-deterministic finite automata, and then we use different automata for different such constraints. In particular, this negation here is useful because we do not need to complement this non-deterministic automaton. However, when we try to incorporate this into the actual algorithm, then it's much better the easiest one to cope is the matrix setting. So instead of using some regular languages, we will use transition matrices of the automata. Okay, so hopefully you know about it. If not, then I will comment on it slightly later on. But if you have a non-deterministic, well, maybe now, if you have a non-deterministic finite automaton, which is on some states P1 up to Pk, then you can model all the transition in a Boolean matrix, which is enumerated by states P1 to Pk, from P1 to Pk. This is a Boolean matrix. And there is a 1 here, meaning that there is a transition from this state to this state, or the other way around. And then the composition of some multiplication of such matrices, or composition of such matrices, corresponds to transition matrices of some longer words. And then from this matrix, you can read whether there is some the word is accepted or not, meaning if there is a 1 from in the column for the starting state and in the row for some of the accepting states. Okay, and this is a natural transformation for the finite automata to be defined. And then we would like to go from this setting of saying that something is or is not in some regular language to specifying the list of transitions for the states. So instead of saying that x is in R, x is not in R prime, then I would like to state what is the transition matrix one for the word which is substituted for x in this first automaton. What is it in some other? Well, this is the transition for the language R, this is the transition for the language R prime, and so on. And of course, this is not a one-to-one transformation, because saying just that the word is accepted, it doesn't specify exactly what's the transition matrix. Saying that it's not accepted, again, does not specify the transition matrix. But we can make a non-deterministic guess at the very, well, or choice at the very beginning, and just say what are the what are those transition matrices for, what should be the transition matrices for the substitution for x. And those choices should be consistent with those describing whether x belongs to those regular languages or not, in the sense that if we have a transition matrix, then we know whether the word is accepted or not. Okay, and this can be formalized as a lemma, saying that if we have word equations with regular constraints of this earlier form, then, well, those constraints are defined by some non-deterministic finite automata, then we can this is NP equivalent, meaning that there is an NP algorithm which transforms to the same equations in which the regular constraints are given by specifying what are the transition matrices for the substitution for x. NP equivalent, meaning that there is a reduction, which is an NP algorithm from one to another. And so in one direction, so when we have the transition matrices, then those already define the regular languages and whether X is in some regular language or not, because the transition matrix already tells you that whether the word which has this transition matrix, whether it's accepted or not. And in the other direction, well, we should guess the matrices. Guess the matrices, check that, and check that they satisfy the constraints. The constraints, meaning that if you know what's the transition matrix, then you know whether the word belongs to some regular language or not. Okay, and as a last thing is that satisfiability of that we give the p-space algorithm for word equations, and in a moment for word equations with regular constraints, but without the regular constraints, there's a typo. Without the regular constraints, we do not know what's the exact computational complexity of the problem. But with regular constraints, it's p-space hard, so the whole problem is p-space complete, because the problem given by, if we are given some finite automata and ask whether there is a word in the intersection of all of those finite automata, or languages recognized by all those finite automata. So this problem is p-space hard. Well, assuming that the number of that this k can be also part of the input, so the k can also grow with the size of the instance. And so since this is a p-space hard, then we could just specify the transition matrices, and well, for x such that the word which is described by that is accepted by all those automata, and then ask whether there is x which satisfies, whether the equation with this simple constraint is satisfiable or not. Or alternatively, we could just list the constraints that x is in language of n1 up to x is in language in nk, and again ask whether this equation x equals x is satisfiable. Okay, so this shows the reduction to our word equations with with constraints. So it's also p-space hard. Okay, so what to do with the algorithm? So we just want to adapt the previous algorithm to the new setting. So of course, when we initialize, when we start the algorithm, then we are giving some alphabet, A, B, C. And for all of those letters, we know what are the transitions. So we know what's the transition for A up to transitions to the last letter, say C. And we know the constraints say what should be the transition for every variable. Okay, and this should of course change when we run the algorithm. So for instance, when we replace x by, say, ax or a to lx, then we do it in the way, then we need to update the constraints, and we update them by guessing some new transition for x. So we guess the new transition for x, well, such that this is still satisfied, so that the transition of this new a to lx is the same as the old transition for x, because we removed this a to l, so it should be satisfied. So what should happen is that transition of a to l times the transition for x is the same as the transition for this old x. Okay, here this row on x is a vector of some transition of matrices, but we multiply them, of course, component wise, because this is a series of constraints. Okay, so that's one thing. And the other is that when we replace some word, be it a pair or some a to l, by a new letter c or by a new letter al, then we need to say what's the transition, what are the transitions for those new letters, and they are, well, natural. So if c comes from, replaces a pair ab, so of course we define the transition for c as the same as the transitions for a times the transitions for b, and the same for this new letter al is the same as the transition for a to power l. So here l could be exponential, but if it's just exponential, then we can multiply the matrices. Well, all the usual tricks that work for multiplication of numbers, they also work for multiplication of matrices. So we can, if we want to compute the Lth power of some matrix, then we can do it in all of log L computation. So this can be done in polynomial time, since we know that this is the most exponential. There is some small catch here, that I'm saying that in the block compression, we replace some A to L, and in the previous algorithm, in order to store this L, then we needed the fact that it's not too large, and I said that this follows from some more general bound, and that this L is at most exponential. And this bound also holds when we allow regular constraints. Okay, you need to, it cannot be stated just like that. You need to actually see how the proof goes and modify a little bit here and there, but nevertheless, it's still true. So even if we allow regular constraints, then the bound on those lengths for the A minimal blocks is still exponential. And this is somehow understandable, because when you think about some regular language R, which is given by an NFA, then if you have an A block, then this means that somehow you're interested only in this language for the unary case. And then if it's unary, then if you want a fixed transition, if you want to specify what's the transition, then it can be, if it's realized, then it's realized by a transition of at most, by a word of at most exponential length. So that's some sort of intuition, and if there are many exponentials, then if you multiply them, then it's still exponential, but you actually need to look into the proof to see that this happens. Okay, so the algorithm just uses those two extra things and everything works, but the problem is that the proof no longer works because previously we used those lemmata which said something about length minimal solutions, and the fact was usually that, for instance, the letters that we use in the in this length minimal solution, they need to appear also somewhere else. Okay, somewhere in explicitly in the equation, or that some subwords, if they are in the substitution, then they need to appear explicitly somewhere in the equation, or at least somewhere in, well, not necessarily in the, well, at least some letters needed from those substrings needed to be in the equation. But this is no longer the case when we allow regular constraints. So it could be that even in the starting equation, when you have some, those are substitution for the variables, that you need some letter B here just to satisfy the constraint which says that y has a B, which can be, of course, specified as a constraint, but it could be that this B is nowhere in the equation. Okay, there are, of course, this could be probably worked around, but in general, it could be that when we say something about length minimal solution, then we no longer can use this argument that all those letters are in some equivalence pairs of some other letters, of some letters which are explicitly in the equation. Okay, and this also does not work for substrings, and this creates some sort of a problem. But so how to think about this problem is that at some point you could arrive at the moment where you have some letter C inside the substitution for X, and this letter C is nowhere else in the equation. Okay, that's the only, or maybe it's at some other variables at some other places, but it's not in the equation. But this letter C, well, it appeared somewhere during the, it could be that it's from the initial alphabet, then it's fine. Then all the time when we use the alphabet of letters which is available in the equation, then we could also add the letters which are in the input equation. And yeah, fine, that's the fixed amount. But the problem is that it could also be that this letter C was compressed from some longer word WC, which was inside the substitution for the variable at some point, but we just compressed it into C. But the idea is that perhaps this was a mistake. I mean, if C is not outside of the equation, then this means that there was no apparent reason to compress it inside the substitution for the variable. If we haven't compressed this C and leave it and just left it with this WC all over the place, then we still should be fine. Well, we would be fine, okay, because there was no reason to compress this C to compress this substring into a letter. Okay, so now what we want to do is just to turn it back. So since this compression was an error, then we just replace every occurrence of C back by WC, which is over the input alphabet. Okay, and this doesn't affect the equation, but we remove this problematic letter and we are back with the letters over the initial alphabet. And all the time you would like, whenever we make some compressions, then we make them, then we consider pairs which are from the alphabet visible in the current equation and from the alphabet of the input equation, which is fine because there are only finitely many. Well, there's a fixed amount of them. Okay, so to this end, we want to supply some homomorphism. Well, homomorphism. Well, just a function which will, for every letter which we have in the current, well, sigma prime is the alphabet of letters in the equation. For every such if we have a solution over some alphabet which could be larger than just the alphabet of the letters which can be seen in the equation, then for every letter in this alphabet, we want to have some substring of words over the initial alphabet. Okay, and the idea is that this was the string which was compressed to this single letter. And moreover, well, this has to be this should respect the constraints in the sense that if we look at the transition for this letter, for some letter B, then it's the same as the transition of the word with which we replace this B. Okay, so the idea is that this alpha on B is the word which is compressed to B, so the transition of this B and the transition of this original word alpha on B should be the same. Okay, and this is stored together with the solution. So now a solution is not only a substitution, but also this additional information. What are the strings that are what those additional letters represent in terms of the original alphabet? Okay, so a notion, one should mention that this is just for the analysis. Okay, so the algorithm, so it's used for the analysis because the algorithm doesn't know the solution, it doesn't know this homomorphism alpha. This is just a tool of the analysis that we use to show some properties. Okay, so this is not stored anywhere. The algorithm works as previously, so that chooses some pairs, replaces, and so on. And the solution and the alpha, they are just used for the analysis. Okay, so to make it somehow more formal, or to make sure that we understand it all, well, that we understand it fully. So the input alphabet, which I will denote by the sigma 0, will be the alphabet which was given at the very beginning. Solutions alphabet are just the alphabet of letters. This is defined for a solution, and those are exactly the letters which are used by this particular solution, together with all the letters in sigma 0 if they are not there. And the equations alphabet are the letters that you can see, well, together with the letters of the input alphabet. Okay, and such a pair, solution and this homomorphism alpha, I will call it a full solution to distinguish it from S, which is just the solution. Okay, so the pair S and alpha is the full solution. And this alpha should map all the letters of the solutions alphabet to strings over the input alphabet. It should respect the constraints, and it should be constant on letters from the input alphabet. Okay, so that's so that we do not make some strange loopholes and do not falsify anything. Okay, so the letters in the input alphabet, they represent themselves. And the claim is that that everything is fine in the sense that if we have any procedure in our original alphabet, in our original algorithm, and there was a full solution, then for appropriate non-deterministic choices, we can define a new, meaning the algorithm makes an appropriate non-deterministic choices, then we can then the new equation also has a full solution. Well, and such that, well, when we compute this alpha on the previous solution word and alpha prime on this new solution word, then this is exactly the same. Okay, so in some sense that the solution word is that we keep exactly the same solution word. And if we forgot about this alpha, then this was shown already. Well, the existence of the solution was shown already, but we only said that, well, either for popping, the solution word does not change, and for compression, the solution word is obtained by, well, appropriate compressions. Okay, so how to define alpha? So if we make any pop, either the popping for letters or for blocks, then the alpha prime is just the same. Okay, because we do not introduce any new letters. Well, we introduce new letters to the equation, but we do not extend the alphabet, so we can use the previous alpha. We knew that S on U is equal to S prime on U prime because we just popped. So then, of course, alpha on S on U is equal to alpha prime on S prime on U prime. Well, because this is just the same function, alpha and alpha prime. Okay, so for this popping, there's nothing there. And for compression, let's say for when we turn AB into C, then what we do is that we assign alpha on C, we assign alpha on, well, on alpha on AB. Okay, so this, which is the natural way, so the string which is represented by this C is exactly the string which was represented by the concatenation of what was represented by A and what was represented by B. And since we also said that row of C is defined such that it's row on A times row of B, then also this extra condition that row on alpha on C should be row of C is still fine, because this was defined so that this is row of A times row of B. This is, of course, row on alpha on A, alpha on B. And then from the inductive assumption, this is the same as row on alpha on A times row on alpha on B. And this is this is this by inductive assumption. Okay, so everything is satisfied here as well. Okay, but this is this should be said that this is relatively easy. So in a sense, so we can think that previously we were working only with length minimal solution, and the only thing that we kept during the run of the algorithm is that there is a solution and that the length decreases. And this was the only thing that we were interested in, because, well, we preserved the solution, and in the end we were able to tell whether the equation is was originally satisfiable or not. And since we decreased the length of the length minimal solution, then we couldn't loop during the algorithm. Okay, and this alpha gives us additional information. So it not only tells us that the solution, well, there is a solution, but that we could still map during our algorithm, we could map the current solution to the original solution. Okay, so the solution of the original equation. And therefore we are able to preserve some more properties. So for instance, do something with this solution even though we no longer have some letters. Okay. So how to use this alpha? So we could use it to remove the letters which are no longer in the equation, which are no longer in equation's alphabet. Okay, so the equation, a solution of an equation is simple if its alpha, well, solution's alphabet is the equation's alphabet. So meaning that we do not use, and the solution does not use any letter which is not in the equation's alphabet. So it's either in the equation or in the input alphabet. Okay, and if the solution is not simple or non-simple, then we can turn it into a simple one, which I will call a simplification. Well, we just remove those bad letters, so those which are not in the equation's alphabet, and replace every such letter C with alpha on C. Okay, so what should be said is that if we have a full solution and we take its simplification, then it's still a solution. Okay, and moreover, it's still alpha defined on those two words, it's still the same. So why? So firstly, if we take look at S on U and S on U prime, S prime on U, then there were some letters C somewhere inside this solution word, and each one of them was replaced by the same word alpha on C. And this C is not in the equation's alphabet, so it's not in the equation at all, so it doesn't appear anywhere on in the equation. So it means that all of those occurrences come from variables. We replace all of them by the same substring, which means that, well, this S prime on U is obtained from this S on U by replacing every such C by a new string, and therefore the same holds for the other side. So they are still equal. If those two are equal, then those two are equal as well. Okay, the other thing is that we want the constraints to be true. So so that the substitution, if we look at the transition on the substitution for the variable, it should be as one prescribed by the constraint. And when we replace C by alpha on C, so alpha should satisfy the constraint that transition on C is the same as transition on alpha on C. So we replace a substring by a substring which has the same transition matrix. So this value does not change. So this is the same as rho on S prime on X for every variable. So again, all the constraints are satisfied. And as the last condition is that this alpha does not change on the previous and the current equation. So it can only differ on this letter C. So originally in the equation, we had some letter C. Now we have alpha on C. So when we apply alpha on both of those equations, here we get alpha on C, and here we get alpha on C. But this string is over the alphabet sigma 0 star. So from the input alphabet, and when we apply alpha on it, nothing changes because it's constant on the equation, constant on the input alphabet. So it's still alpha on C. And so indeed, this nothing changes when we apply alpha on the new solution word. Okay, so what's shown here is that when we have a solution, a full solution, then we can replace it with its simplification, and it's still a valid full solution. Okay, and this removes our problem with having some letters inside the solution which is not in the equation's alphabet, because we can always simplify the solution. Okay, so now our algorithm will look exactly the same as previously, so that we iterate, we choose the letter and either uncross pairs or uncross blocks, and just apply those extra operations that we need to compute we need to update the transitions for the variables and for letters. There is some very small extra initial information, because it could be that our instance doesn't have any letters at all. I mean, there are no letters visible in the equation. Just because of that. And originally we said that then this means that it reduces to equations over to Diophantine equations, and this is no longer true in this case, because some letters need to be used because of some regular constraints. But now when we pop some letters into the equations, then we can ensure that there are letters in the equation, so we can list them and make the compressions. Okay, but there is a problem because previously the idea was that on one hand we keep the equation small, but at the same time in each compression step we reduce the length of the length minimal solution. And this is no longer the case, because when we simplify the equation, when we simplify the solution, then it could be that we replace some letter by some very long string. So we lose this property that whenever we make some in each step we reduce the length of the solution. So there is no guarantee that we will terminate at any place, because we could go to the same equation and compress something, but in the meantime also decompress something and arrive at the same equation with exactly the same substitution for the variables. Okay, but luckily this is not the case. We just need to somehow change the way that we look at what's the length is not the best option to. We shouldn't look at the length, because it could now increase as well. But instead of that, we look at the weight of the solution. So we look at the length, but we add also the length of the solution word, but we also apply alpha on it. So in some sense, we look at the length of the equation, but in terms of the original solution. Okay, and to be precise, we do not look at the solution word, but only how much this alpha on. We look at the substitution for x, apply alpha, so what's applied to it in the original equation, and also add, multiply it by the number of this x appears in the equation. So in a sense, we look at the solution word, and for the parts which are inside the variables, we look at the alpha on s on x. So we look for those words and apply alpha on them and count the length. And if something is explicit in the equation, then we just count the length. Okay, and the claim is that this weight decreases during every possible operation, assuming that something changes. And why it's not? So essentially, pop decreases the weight because a letter, during popping, a letter moves from this part. It's calculated, it's counted here, and it's counted here with multiplier 2. So a letter which is counted, which is in the substitution for the variable, is introduces at least 2 to this part. And when we pop it, then it also only introduces 1 for every occurrence of the variable x here, which means that this popping decreases this weight. Okay, at the same time, when we make the compression, then the compression could decrease this part, but it doesn't affect this part, because when we compress AB, then alpha still assigns this new letter the same string as originally, so the compression does not affect well this second part. Okay, and here can decrease the decrease those 2 stars. It could keep it the same if there is no compression, but it could also decrease it. Okay, so actually this is somehow different from the previous approach, because now the weight of this invariant, which says that we are somehow getting smaller all the time, it actually counts. It depends on the fact that we pop letters from the variables, not on the compression, but on popping from the variables. But okay, it's fine that it works. I mean, anyway it works, it's fine. Okay, so those are the lemmata. I already said it previously. So if we make all the sub procedures that we consider, if we make, they do not decrease the word, and if something changes in the equation, then the weight is decreased, which means that exactly the same argument, which counts exactly the same argument could oh, sorry, this is for the length of the equation. So all the time during the running of the word equation, using exactly the same argument as we used previously, we can ensure that the length of the equation is at most quadratic. So there's always a choice of a pair to be compressed, which could be, it's either non-crossing or crossing if it's crossing the draft, only linearly many occurrences, which shows that all the time the size of the equation could be at most quadratic. Okay, the proof is more or less the same as previously, which shows that this generalization of the algorithm also works in quadratic space for the variant with regular constraints. Okay, and that's it for the regular constraints. I have 2 remarks here, that this approach with using alpha, so with substituting back the original substring, it's not the shortest solution that could be to this problem. What we could also do is we could actually increase the input alphabet by introducing letters for every, well, a letter somehow indexed by the transition vector for every possible transition vector of matrices. Okay, and then when we pop the letters, we could also pop those fake letters to simulate some longer substrings, and if something doesn't appear in the substitution, then we could substituted by one of those new letters. There are some problems there, but all of that could be also, all those details could be worked out. But the thing is that this approach with alpha is actually more useful later on. It's useful also in some other cases, so it's better to somehow better to introduce it. Alternatively, so this length minimality, that the minimality that we used for the equation, for the solutions, is that we are looking on length minimality, and then for length minimal we can show something about the crossing pairs. We can show that the substitution for that the length of the exponent of periodicity, so the length of the A blocks, is at most exponential. But this length minimality doesn't really work well with other properties. For instance, preserving the regular constraints. But we could also develop some different notion of minimality, and there's also minimality under homomorphisms, which means that which was originally used by Plantowski also for regular constraints and for some other applications, which means that a solution is length minimal in this homomorphism setting, meaning that it cannot be obtained from a different homomorphism by applying something on top. And this applying something on top could be replace C with AB, or replace a letter A with ABC, with DEF. So in general, we need something non-trivial. So a permutation of letters or some cancellation of letters does not count, but that some of the letters could be replaced by some longer substrings. Okay, and this type of homomorphism is actually preserved by those all of those compression operations, and then all of this theory, all the properties could be shown for those homomorphism minimal solutions. But the problem is that this is much more technical, and showing that they are actually preserved requires work, and in the end, it turns out to be longer and much more approachable. Okay, so this alpha approach is since better. Okay, so it's almost time on one hand. On the other, this is I think good moment to stop. So I think that if we can make this 15 minutes break at the moment, then it would be slightly better than for me to begin and make a pause at some arbitrary place. So are there any questions regarding this regular constraint part?
Well, I have a couple of questions. So the first question is, so suppose we just have regular constraints, but we are not interested in the minimal solution. We just want to check that it exists. So then everything is just really simple, right? Or you really need to do this computation of this, well, the translation between alphabets.
The problem is that we do not want any. We cannot make an argument. We need some sort of argument in order to show determination. We need some sort of argument that we do not loop.
Ah, right.
And it could be that we arrive at the same. If we do not make the replacements, then we need to know exactly what's the allowed alphabet of letters. So that if we say that we want to pop the first letter, then from which alphabet? And if we just keep track of all the letters that we introduced, then we never go back, we never loop, because all the time we collect more and more letters. Okay, so we need to somehow trim the number of letters that we are using in our solution.
All right, but if we just get to the basic algorithm without the constraints, then yes. Then at every non-deterministic step, you reduce the total length, well, the total size of the equation in the number of symbols, right? So the alphabet
for the equation, not for the solution word, yes. For the equation, not necessarily, because in some step it could get slightly larger, then smaller, and so on. So for the equation, we do not guarantee that there's also a decrease of length. For the solution word, there is a decrease of length.
Ah, I see. Yes. So that's why you really need to take care of this, well, of the length of the solution in this generalized construction, because otherwise you don't have any parameter that is, well, that is reduced, right?
Yes.
Yes, yes. Now I see, because I thought it's a little bit simpler.
So moving into something else, into some other extension, is that we would like to extend this algorithm for from the case of sigma star to the case of semi-group over the same alphabet of the free group of the same alphabet. So we move from this sigma star settings of the semi-group or monoid, if you like, to the case of groups. And just to be sure, when I'm talking about a free group, then this means that we have some fixed alphabet or the generators, and every letter has an associated inverse of itself, which is different than the letter itself. And we have reduction rules, which we can transcribe a to -1 into an epsilon. And we are looking on the reduced words, so the words for which such rule cannot be applied. And every word has a unique reduced form, which is easy to show, but well, easy but time-consuming to show. And the free groups consist simply over some generators, consist of all such reduced words. And the multiplication, we take the words and we make all those reductions afterwards. Okay, this is well defined. This defines a group. There is a alternative way of saying why it's called the reason why it's called a free group is different and comes from some universal algebra, but doesn't matter that much. This is the free group. Okay, and I will usually use just the words, even if they are not reduced. There is a unique way, words as elements of the free group, because there is a unique way in which they define an element of the free group. And the word equations in free groups are defined in the same way. So we write some equation where both u and v are words over the alphabet. This means, well, sigma letters of the over the generators or the inverses of the generators and x's like that. And then the only difference is that when we talk about the solution, then this solution means that the equality here holds in the group. So for instance, which means that there could be more solutions. For instance, if we look at an equation ax equals b y, then it doesn't have a solution as a in the previous setting, but here we could substitute x equal a to -1, y equals b to -1, and then a minus 1 equals b minus 1, because all of those are equal to epsilon. Okay, or 1 in this setting. I should probably write 1, but nevertheless, they are equal. Okay. And the idea is that this setting, that those could still be interpreted as equations over semigroups. So first of all, when we move to the algebraic setting, then for the sigma star without any cancellation, I will usually say that this is a free monoid or free semigroup, in the sense that the only operation is the concatenation, and we concatenate some two letters, and this gives us AB. Again, it's free. For some reason, it's free. The difference between the monoid and the semigroup is that in the monoid we assume that there is an epsilon, and for the semigroup we do not assume that there is an epsilon, but in our setting we have an epsilon. Okay, so it's a monoid. But the only thing, the thing that this free monoid or free semigroup misses when we compare it to group, well, it's not only the cancellation, but also that the inverse operation changes the word. So if we take the inverse of a b to -1, this is b to -1, a to -1, and there is no way of simulating this inverse operation in the group, in the semigroup, and we do it by adding some additional operation of inversion into the semigroup. So in the inversion is some formal operation on the monoid or on the pre-semigroup, such that if we apply it twice, then it gives us the same word. And moreover, if we apply it on multiplication of two elements, then we just split and apply it on every of those elements separately. And this works for arbitrary words. Okay, this definition Such an operation is called a bijection for an arbitrary monoid, but we use it just for the free monoid. And there is no outer meaning for this involution. So it could be that we say that for every letter, the involution is the same, meaning that if we apply it on the word, then this is just the same word reversed. Or we can use exactly the same thing as for the free semigroup. So we have a separate letter a and a to -1, and then if we take the involution, then we just map the letter to this inverse. Okay, and the word equation, and of course, when we are giving a free monoid with involution, then we can define word equations over them. And the definition is again as previously, but the additional thing is that for every variable, we also have this inverse of the variable. We allow the inverse of this variable, and we want that the substitution for the variable and for the inverse variable, there are inverses of each other. Okay, so for instance, if we say that x is equal to the solution for x, substitution for x is equal ab, then the substitution for inverse of x should be inverse of b, inverse of a. So this is the inverse of ab. Okay, and great. And the reason why we are considering this is because it's well known from many years already for many years that if we want to solve a system of equations, or just a simple equation over a free group, then we can turn it into an equation over the free monoid with involution. Okay, and moreover, it's not only that the satisfiability is preserved, but actually there is a bijection between solutions. But this is somehow there is a caveat, because we do not allow factors. So for the free groups, we can always assume that substitution are reduced, but for the free monoid with the involution, we need to assume that for the bijection to work, we need to assume that there is no factor AA. So there is no thing that we could cancel or reduce if this were a free group. Okay, and this factor is not only in the substitution for the variables, but also in between letters and in between variables or variables and letters. So we do not allow such factors in the solution word. Okay, so if we look for S on U, then it shouldn't have any factor of this form. And so a slight note here is that if we have a solution, if this free semigroup has a solution which has such a factor, okay, we transcribe the equation. We are given an equation over a free group. We write some equations over a free monoid with involution, and it could be that we are able to find an equation which is not reduced, so it has such a factor. So it has such a factor, but then this solution is also a solution over the free groups, because then if we cancel out all such factors after the substitution, then we still get a valid solution. Okay, the cancellation is the same on both sides. Okay, so this is a restriction only in a sense in a one direction. So it could be that if we have a solution of this in the free semigroup, then this is also a solution over the free group, but it's not necessarily the other way around. So the difficulty in the construction is in the other ways, in the other direction. So if there is a solution over the free group, then we should be able to construct a corresponding solution over the free monoid with involution. Okay, and for that I need a separate piece of paper to and this is done relatively easy. So firstly, we make sure that each equation is of the form either xy equals z or x equals a letter a, and this is easy to be done, because otherwise, if we have some longer equation x a b y z something, then we just partition. We introduce a new variable, say x1 for the first part, x2 for the second part, and we replace whatever it's written here with x1, x2 equals alpha, and we write a separate equation xi equals this something xab, x2 equals yz something, and we continue with this process. And since each time we just split the existing substring of the equation, this increases the size linearly. Increases the size linearly. Okay, so we can assume that the equation over the free group is of this form, so that each equation is either, well, triangular equation, I think this is usually called, or it just says that a variable is equal to a letter. And then when we have an equation xy equals z, this is over a free group. So if we look at the substitutions s on x, s on y equals s on z, then what happens is that the substitution is of the form that there is a part, some prefix of this s on x, there is a suffix of the s on x, a prefix of s on y, suffix, and those two cancel out. Okay, so there's a maximal suffix of x such that it cancels with the prefix of y, and otherwise the z is equals to those to those two parts. So we add an extra equation that x is equals to x prime r, y is equal to r involution y prime, and that z is equal to x prime y prime. And then this system of equations is satisfiable over, well, those sub-equations are satisfiable in the free group. With the involution, well, there is a bijection between solutions of this equation and solutions of those equations we do not have any factor AA, because we just take this R to be maximal suffix of X, which is which cancels with the prefix of Y. Okay, I mean, there are perhaps some small tiny details, but otherwise this is fine. And we do it for all equations in parallel, of course, introducing new R's all the way. And therefore we, in this way, we change one of those systems of equations into another. Okay, so what to do with those free semigroups with involution? We know that that's enough to be done. So we essentially use the previous algorithm, and in the analysis, we also use this extra alpha. So the idea is that what are the extra difficulties? So what happens if we just try to, if we were to run this original algorithm on this involution, in the variant with the involution? So first of all, we know that it should hold that s on x involution is equals to s on x involution. So if we replace x with some, well, we pop something to the right, left and to the right, then we should also do a corresponding action for the involution of x. So we should pop the involuted part to the left and right, so that the substitutions for those two parts are still involution of each other. Okay, and this is easy. So whenever we do the popping, we need to do the other popping as well. And if perhaps we are doing the two of them in parallel because of some uncrossing, then we just need to coordinate that they popped exactly the same letters. Okay, this is fine. There are some more letters introduced into the equation, but this just affect the constants. The other problem is that if we compress some per AB into, let's say, into C, then we should also compress the other part. Well, because it could be that we could even write an explicitly such an equation. Well, we need to essentially guarantee that if something is compressed, then its involution is also compressed. Because it could be that we are writing something like x involution is equal to some string w, we replace AB here, so we need to reduce, replace corresponding C here, so we need to introduce the involution of C for x, and then this means that here on the other side we need to also compress this B involution, A involution into the C. Okay, so whenever we compress AB into the letter C, we also compress BA into the letter C involution, or C bar, which is perhaps easier to say. And this is fine as long as they do not overlap. So we want to make all those compressions in parallel, and this of course can be done, but it cannot be done if they overlap. So if A is equal to A bar, which in principle could happen, then it could be that we have something of the form BA, BAB, which is the same as B bar, A bar, B, and then at the same moment we would like to as AB we would like to compress this, and as a involution of the AB we would like to compress this, and of course this cannot be done. And there are many different ways how we could deal with that, but the simplest one is to observe that initially that this can happen only if there is a self-involuting letter. Okay, so the letter such that the involution on it is exactly the same letter, and this does not happen at the very beginning. Okay, so initially, since we start from a free group, then involution is the same as inverse, so there is no letter which is involuted to itself. So this cannot happen. And later on, if we were to introduce some self-involuting letter, then this could either happen when we compress a pair AA into a new letter, into a letter C, but then, okay, this is one case, and the other is that there is some A to L which we would like to compress into C, and again, this A to L is equal to, well, it's self-involuting. But in this case, it depends. It can be shown that either, depending on whether L is even or odd, then either if it's odd, then the middle letter is already self-involuting, which cannot be, and if L is even, then it means that in the middle there is something like a bar next to each other. So if there is no factor A to A bar, then we are again fine, because no such compression could occur. I mean, there is no way, then there would be no way to introduce actually the self-involuting letter. Okay, but this factor A bar shouldn't appear, because since we reduced from the 3 semi-groups, then our reduction, if there was a solution, then after the reduction for the solution of the 3 semi-group, there is no, first of all, self-involuting letter, and second of all, there is no factor A bar. Okay, so, and then we would like just to keep this invariant during the algorithm, which would guarantee that there is no self-involuting letter in total, so those overlaps can be avoided. And in order to do that, then we need this alpha which we had. Okay, so as I said previously, that it's useful later on, and this is again the moment when it's useful, because it allows us to somehow show that nothing but how to keep the invariant true. Okay, so what we want to show is that, and can be shown, is that if we have a full solution and we want to such that there is no self-involuting letter and there is no well, cancellation somewhere inside the solution word or in alpha on the solution word, then if we make any sub procedure which can perhaps could be popping or compressing of some substrings, then afterwards the same holds. So first of all, the equation doesn't have it, the solution word doesn't have it, and also when we applied alpha, then it does not have it. So for the alpha, that's easy, because alpha prime on S prime on U prime should be the same as alpha on S on U, which means that since it doesn't change, then it still doesn't have any self-involuting letter, neither AA. For the popping, it could be that we introduce such a letter due to popping, but we know that it doesn't appear in the solution word. Okay, so this AA bar doesn't appear in S on U, so also due to popping, we shouldn't introduce it if we were to make the choices according to this solution. And the last part is that it shouldn't be in the it should not appear in S prime on U prime, so in the solution word. So it could be that it was introduced either a self-involuting letter or this well, cancellation was introduced due to compression. So there could be some pair like that, and this A is a new letter. Okay, but since it was obtained from a compression, then for instance, if it was a compression of BC, then this A involution is C bar B bar, which means that this should this couldn't be, because this was already a problem already before the compression. Okay, then perhaps some simple, well, I missed some small case, but essentially the proof goes like that. So assuming we have this extra information on alpha and we keep the invariant all the time, then it can be shown that we do not introduce any such problematic words. Okay, so this simply means that the whole algorithm works. So we can perform exactly the same algorithm, adding those extra treatment of the involution, and the same proof still works with this alpha, which shows that the algorithm works in P space. Okay, so what I haven't said, any questions here? Because this is, again, we will move to some extra, to some new improvement right afterwards.
Well, maybe just a very, well, kind of simple question without much thinking. And can you combine the two extensions to have the free groups and regular constraints?
Yes, it can be done, although there is some technicality that if you look for regular constraints, then for the groups, they should be consistent. So if you regular languages over groups are not exactly the same as regular languages over semigroups. So for instance, if you define them using those transition matrices, then it should be true that there is some involution, and that if you make the constraints on the involution of x, then it should be the same as the involution of the constraint for x. So there is some there are some extra conditions that need to be satisfied for the regular constraints. Okay, but in principle you can do it.
I see. Yes.
For the groups, for the semi-groups, there are no extra conditions, I think.
Yes.
There is another thing, another possible extensions is that, well, this idea that we treat semi-groups assuming that there is no self-involuting, well, there are no self-involuting pairs, and there are no, well, those cancel no A bar. Well, this works if we want to treat, if we treat it just a tool to show the result for free groups. But in general, this might not be the best. Well, you might want more. For instance, there was at some point, there are some problems on nodes on graphs you solved using those word equations, and with involution, and they explicitly used also the involution, which allowed such setting, and they had allowed self-involuting letters. And the idea is that so then it's no longer true that it cannot be that the pair AB overlaps with B bar A bar, because it could be that that's the same letter. Also, A could be the same letter as A bar. For instance, if you just use the reversal, then everything is a self-involuting letter. And this can be solved by combining those two operations of pair compression and block compression, and we are just looking at substrings of the form we just have alternating letter A and B. Okay, so we are compressing blocks of A's, that's one thing, but we are also, instead of pairs, we are compressing such sequences which just alternate A and B. Okay, so essentially this is an AB and BA compression at the same time. And then they are well defined in the sense that they do not overlap. So because if they were to overlap, then they could just be extended. And it's more or less the same. So since those are just two letters, then you can make the compression as if it were as you make it for block compression, and everything works. Okay, but this is needed only when you allow self-involuting letters. So for the presentation, it's better just to skip those, well, easier to skip those letters. And of course, some special treatment is needed when A is equal to A bar, but B is different than B bar. And then you need to also compress some triples like ABA or AB. No, not this one, this one. AB A bar, because this is the pair AB, this is this involuted pair, they can overlap, but this overlap cannot be extended. So there are some other sequences that need to be compressed, but everything can be can be done. Okay, some slide, another a different type of extension. Okay, so I would like also to comment something on block compression, since there is time, not very much time, but enough time to say some things. Because there is, if you aim to any sort of efficiency when you try to actually to implement it, or if you want to make it deterministic in some setting, then some of those sub procedures can be made. Oh. Sorry, I pressed the wrong key. No, sorry, this is this different order than I wanted. So at some point I told you that the maximal blocks of A's are of at most exponential length. But at the same time, if you think about it, then those lengths are not that much needed. So if there is a variable and we pop some A to, let's say, 150, and there is some Y, and there are some explicit letter A next to it, and there is some Y, and we pop A to 152. Oh, and at some other place there's A to 70, A to 70, A to 72 popped from some different variables. Then the only thing that really matters here is that those blocks of A are of the same length. Okay, those are actually not. Now they are of the same length. The only thing that matters during the block compression is that they are of the same length. Okay, and afterwards they are replaced by the same letter. So the fact that this was 152 was important for a very short moment, and afterwards it's only important that they were the same. Okay, so if those lengths were somehow completely different, then it would still be fine, as long as those are the same. In the end, we would get the same lengths. Okay, so instead of explicitly giving those lengths, we would like to say that, well, if you look at the block which is of length, if we forgot that those are explicit numbers and we were just to describe them as what was popped to the right from X, what was popped to the right from Y, what was popped to the right of Z and to the left of Z prime, then we just wanted to say that Rx plus 2 is the same as Ry is the same as Rz plus Rz prime. Okay, so the fact that they were equal, this is formalized using some system of equations. Maybe to make it somehow more concrete, if we look at the equation Ax x equals x a y y, then this can be separated into two equations because this is the same length as this one. The first one ensures that we are looking at, maybe let us put b here as well. The first one ensures that x is, we have only letters of a inside x. And the second here says that if the solution for x, substitution for x is a to Lx, is the substitution for y is a to Ly, then what only matters is that 3Lx is equals to 2Ly. Okay, so that those lengths satisfy some constraints. So just let us try just to do it. So let's try to forget all those actual numbers and try to focus just on the lengths and how they are defined and what can be said about them. Okay, so we can only say something about the blocks which are either visible or almost visible because they are at the end of the variable. So I will say that a block in the solution where it is touching for this solution, either it has an explicit letter, so we can somehow observe it, or it's an a prefix or a suffix. The reason why we introduced the a prefix and a suffix is that it's somehow important that the variable begins with a. If we declare that it begins with some different letter, then perhaps the solution would look completely different. But just by saying that it should begin with the same letter, we somehow affect the solution. Okay, so we want to speak about the blocks that can be observed by either some of the letters are already in the equation, or there are prefixes of suffix or suffixes, because they are somehow affect the equation as well. And of course, and the touching length is just the length of such a block. And of course, there cannot be too many such blocks, because they use some letters from the equation, or they use the prefix or suffix of the variable. So at most, the number of letters in the equation plus 2 times the number of that, or plus the number of, or 2 times the number of variables. Okay, and it can be again shown that for a length minimal solution, if you look at then every maximal block has a touching length. In particular, those a prefix and a suffix are actually important. So it could be that you cannot observe it anywhere else. Okay, so how to replace those explicit lengths with some, well, with equations, with parameters. So we look at the solution word, and we look at the blocks of A's, and there are some, well, we just list the numbers from left to right. So this is E1, E2, E3, E4. They are of course the same on the left and right, so we could just wrote it in one part. And also look at the substitution for the variables, and we denote by LX and RX the lengths of the prefix and suffix of the A suffix and A prefix of the variable. It could be that this is 0, then we could just disregard it and throw away the variable, but just for the sake of consistency and to streamline the argument, I will just use that LX and RX, even though some of those do not appear. So for instance, in the example that we had previously, so this is the length of this would be LX. The length of this, let's say it's maybe do not assign a concrete letter. So this block is of length LX plus 1. This block is of length 2LX plus 1. This is of length LX plus 1. And this is of length 3LY. Actually, it's a different equation, because here it has A, and here previously it was X. Okay, so the lengths of the maximal blocks are like that. And for it to be a solution, so we could say if Lx is equal to 1 and Ly is equal to 1, then this defines a solution. Okay, so we are going to produce some arithmetic expressions somehow connected with those equations, and they have some, instead of saying what are those systems and then say what are the properties, so maybe what we would like to say, some very mild properties that we constraints that we want to be satisfied. And I will say that the system is a system of small arithmetic expression. So first of all, it will use only variables that are connected to, well, to the variables of the word equation. So Lx, meaning that, well, the length of the prefix, Rx, meaning the length of the suffix. The sum of constants is not large, so the sum of constants is at most n, where n is the length of the equation. And if we count how many times the variable Lx and Rx are used, then they are used at most as many times as this original variable x is used in the word equation. And this counts the multiplicities. So we only allow positive constants, positive natural constants. And if there is 2Lx, and 3Lx somewhere, then we want to know that this x, original x, appeared at least 5 times. Okay, and the arithmetic equations that we allow, they will use constants, these variables Lx, Rx, overall variables in the equation, and, well, coefficients are, as written here, coefficients are positive. Constants are also only positive. And what else? I think that's it. And for the value, if we have some arithmetic expression, well, some phi, then when we substitute it with L, well, small l, small r, x, for x in the variables, Well, the meaning is should be clear, so that we substitute the variable lx with this fixed number lx, and we substitute variable rx with this fixed fixed number rx, and just evaluate this whole arithmetic expression. Okay, so the last step is how to actually construct such arithmetic expression from the equation. So we look at the equation, and well, there are the variables somewhere here, let's say x, and we look for maximal blocks of a, which appear somewhere here. So let it be ei. So, and it consists of some letters which are in the equation and of some letters which are prefixes or suffixes. So if it includes the prefix, well, the suffix of x, then we include the corresponding variable. If it includes some C letters here which are explicit, then we add the variable. Let's say if it extended here to the variable y and it included all the prefix of variable y, then we would add the prefix of y and so on. And it could be, of course, that one block of a could span over several variables if we are lucky and all the letters between them are just a's, and the substitution for the variables are also just a's, then, well, one block could span over several variables. For instance, in our equation, well, the one that we had before, x equals x, y, b, y, 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 then here the arithmetic expression would be lx plus 1. This one is 3lx. This one is again lx plus 1. And this one is 2ly. If it were no b here in between, then there would be only one expression on both sides, and therefore the length would be like that. Well, the arithmetic length would be like that. Okay. Okay, and what we have constructed is small. Whatever was the definition of small, that's fine, because we add something to the arithmetic expression. For every constant we add at most 1, so the sum of constants is 1. The variables are as defined, and moreover, well, since we just scan from left to right and construct those arithmetic expression, this means that a variable, well, this lx is used at most as exactly the number of times as x actually appears somewhere in the equation. Okay, and this is defined in a way so that the length of this ith block is exactly this arithmetic expression substituted with the actual value of the length of the prefix and suffix of the of the equation. Okay, so for instance, again, if we have this equation x, y, b, y, y, for instance, with x, so solution for x would be a squared, then the solution for y is a to 6. The equations here are lx plus 1, not equations, arithmetic expressions are lx plus 1. Here it is 3lx. This again lx plus 1. This is 2ly. And if we substitute to those arithmetic expressions the values of the prefix and suffix, then this would be 3, this would be 6, this would be 3, this would be 6, and those are exactly the lengths of the a maximal blocks inside of this equation under this substitution. Okay, so this would be a b, a. Okay, and if we cancel this b, I mean, if we consider this equation with no b, then there would be a sum here all the way, and the value is actually 9, which is the length of the unique maximal a block for that equation under this substitution. Okay, and from I forgot something. So now we can construct a system of equations, which I will call D, which looks in a simple, very simple way. So for a fixed solution, so when S is fixed, so the equation looks as follows, that if those EI equals IJ, so if two maximal blocks are of the same length, then we add an equation EI equals EJ. Okay, and that's it. So that those are, to make it somehow simpler, then we do not make too many duplicates. So if there are, say, 5 blocks of the same length, then we just make 5 equations or something like that. We do not give it for every possible pair, just the minimal, just somehow the minimal number. And then the claim is that those are the maximal okay, that if we have some lengths of maximal blocks and the corresponding arithmetic expressions, then this gives a system of equations D. Then if we have any other solution of this system of equations, then it preserves the preserves the equality. Okay, so this if we substitute those other values to this system, then we would still get the equality. And this is true just by the definition. So if EI was equal IJ, then we added an equation EI equals EJ or something equivalent, like a chain of equalities which implied this one. So if something is a solution, then in particular it satisfies this equation. Okay, so now instead of thinking of a fixed solution, we can look at some parameterized solution. So instead of having a to some fixed power, let's say 12, we could look at some parameterized solution which have a to power lx or a to power ei, which are arithmetic. This is capital L. So we can have a to some parametric power, and we use them exactly the same. We define them similarly, well, naturally. So if we look at the substitution for x, and there is some maximal block of a, so we just replace it with appropriate letter. So if this is ei, then we, if this is the if maximal block, then we replace it with a to ei, or if this is a suffix, then we replace it with, which was of length lx, then we replace it with a to lx. And then when we, of course, we can define what's we can apply such substitutions on U and define the reduction rules in the natural way. So if there are two blocks of a's to some arithmetic powers, then we can combine them and other arithmetic powers. And then it turns out that by some simple induction, that if you look on S on U, and if S on U at some place had a block of length EI, then this S on U has a block of A to EI. Well, because this is the way it is defined. So we replaced those arithmetic expressions are defined by looking what's being used by this maximal block, whether this is a suffix or some constants. So if you just replace in the substitution the suffix lx, if we replace it by the variable, then in the end this maximal block a to ei is replaced with this with this a to some parametric power. Okay, and then we can define instances of those parameterized solution again in the natural way. So if we have somewhere some a to some parametric power, then if we apply it if we substitute the variable by some concrete numbers, then we should substitute this parametric power by appropriate numbers. Okay, so, and then this is indeed a solution. This is a well-defined substitution in the sense that it doesn't have, this is a true substitution in the sense that it has no parametric powers. And moreover, if we use those original values of the lengths of the prefix and suffix, then we actually get this solution that from which we started. But again, this is just walking around with the same idea. So we replaced lengths by their abstractions using variables, and if we substitute those variables but by those true values from which they were constructed, then we obtain this original original substitution. But this is also in the other direction, so that if we have any other substitution of this system of equations D that we constructed, then this parameterized solution in which we substituted the variables with those actual values, then it turns out to be a true solution of the word equation. And why it is that? Well, because of the second part. So if there was a length, anything with the length E, then it was somehow obtained from length of the prefixes and suffixes. So if we substitute it with the values Lx and Rx, then this corresponds to the to the prime. Then this corresponds to the substitution in which those were the true values of the prefix and suffix, and the corresponding maximal blocks were also of those lengths. And the thing is that if some two maximal blocks in this for the solution S, if they were equal, then under this substitute then we added an equation EI equals EJ, and then since this L prime and E prime are those values are a solution, then this means that if we substitute them to the equation, then this equation is still, well, then this is satisfied, so that those two lengths are, so those two values are still equal, which means that what we do is that we replace this value EI by the value of, well, this corresponding arithmetic expression on those values. And so if we look at the equation, then those two different maximal blocks were of the same length EI and EJ. So when we substituted, when we ensured that those in the parameterized solution, this was of length EI and EJ, and those are arithmetic expressions, and if we substitute those different numbers, then we again, since this is a solution, then we ensure that those two values are still equal. Okay, so now for this improved block compression, instead of, maybe just in one sentence because I'm running out of time, so instead of compressing explicitly, we could just pop those numbers, make the maximal blocks, make the system of Diophantine equations, verify whether it's satisfiable or not, and if it's not satisfiable, then we reject, and if it's satisfiable, then it means that an arbitrary solution of those of the system would lead to a true we could simulate an arbitrary solution of the system. Sorry, then we can make the compression, because this is equivalent to making the compression for those values that we guessed. Okay, I think it's I'm not going to make it any clearer. Then let me stop here, and if I could also answer some questions tomorrow, if there are some questions regarding this part.
Yes, I must say this was a really difficult part.
Maybe shouldn't have tried to do that.
And so, well, just well, maybe the thing I didn't understand was really so basic that I should have said that before. And how can you consider this just this repetition separately of the pairs?
Well, wait. What repetition? What pairs? This was a long time ago. What pairs?
Well, as a matter of fact, I didn't understand anything. So, well, because everything seems to be unary, beginning from some point. And unary means this compression rule where you compress A to L to A sub L, right?
Yes.
Yes. But how can you separate unary? Because to me, it looked like you have this unary compression and the pair compression just, well, concurrently there, well, they always, both of them happen. And here somehow you have isolated.
Wait. I probably didn't make something clear. So what I was saying here, so this Moron block compression, this is a variant of the block compression for the original alphabet. So not the one implied for the, not the one used for this involution variant.
Yes. Well, then I must say I didn't understand anything. Well, beginning from this point, yes.
I can only take the blame on myself.
Well, the problem is, of course, the time too tired and too stupid, but maybe our colleagues understood it. So this would be a relief to know.
I think that what happens is that we just try to understand how the maximal blocks in the minimal solution, within X's look like, express them through Lx and Rx, which then find the solution, like find the solution to this system. Like we know the sum maximal blocks of us A's must be equal. Find the solution to LXRX and then just if we can check it.
Yes, but then the last thing is that we do not actually need this, actually use the solution, since if it exists, then everything is fine.
Yes, okay.
Okay, so this is what I wanted to show, and unfortunately didn't manage properly enough.
Well, I would say to make me understand is always a much more difficult problem. You know that for years. So it seems that yes, if there are no more questions, then we're done for today. And the next lecture is tomorrow.
And it will be about terms.
About terms. So that's an extension from words to terms. Well, it's not an extension. These are words are basically terms with associativity, right? And one associative operation.
Yeah. Well, but it could be also looked as terms over a unary signature, so that all the letters have signature 1.
Ah, so you just concatenate them in one order. So, and what kind of terms will you have?
Well, arbitrary terms, like that you could have
right. So
F on A on X on F on A B equals something like X on G on D.
I see. So if terms are unary like F sub A small, meaning concatenate A small, then this would be just strings.
Yes, if there are no symbols of larger arity, so every letter is A.
Right. Yes, then they're just
X.
Yes.
On C. And this is the case of words. But here we allow we allow larger arities of functions, and the variables still take some arguments. So that's
terms like trees, not bamboos in some sense. Like words are bamboos labeled with each element labeled by some symbols, and
yes.
Well, so then, well, yes, thank you very much for the lecture. At least I hope I was able to follow most of it, more or less, after the extent I'm able. And well, and Vladislav was able to follow everything as usual. So then we continue tomorrow at the same time. Well, I think that's it.